All right, covalent bonds. A covalent bond occurs when two nonmetals try to form a bond together. Both elements are very attractive to their electrons. They both have high effective nuclear charge. What that means is that they can't steal the electrons from each other. So when you have an ionic bond, you have a metal and a nonmetal. The nonmetal likes electrons a lot, and the metal is willing to give up its electrons, so you have somebody that donates from one to the next. But when you have two nonmetals, they both are too attractive to their own electrons for one of them to act as the donor for the other. So let's say, for example, like our carbon tetrafluoride example here. Carbon likes its electrons and fluorine likes its electrons. Fluorine likes more than carbon, but not enough more that fluorine can actually rip those electrons away from carbon. So what they're stuck doing instead, since one isn't willing to give up its electrons, is they're stuck sharing. And so these two electrons get put in between the two atoms in a shared position, and this bond is particularly strong. It holds the two things together, and as a result, they get stuck together in what we call a molecule. So let's look at this from the perspective of their Bohr-Rutherford diagrams. First of all, carbon. Carbon is 6, 12, so its Bohr-Rutherford diagram is 6 protons, 6 neutrons, 2 electrons in the first shell, and 4 electrons in the next shell. Okay, now these 4 electrons on the outside are shielded by the 2 electrons on the inside, so to get my effective nuclear charge, I have plus 6 minus 2 inner electrons, leaving me with plus 4. And so from a bonding perspective, what this looks like is plus 4 in the middle with 4 electrons hanging around the outside. Alternatively, tetrafluoride, fluorine, do it down here, fluorine has 9 protons and 19 total mass, so 9 protons and 10 neutrons. In its first shell it has 2, and then in the next shell it has 7. The 7 on the outside are shielded by the 2 on the inside, so we have a plus 9 minus 2. We have plus 9 in the nucleus, shielded by 2 electrons, for an effective nuclear charge of plus 7. And so what we get is we get a plus 7 with 7 electrons around it. So let's just, I'm going to move that up. Let's put them straight into the bond when we draw them. Oh, hold on. Go back to the pen. Okay, so we have our plus 7. That's our fluorine nucleus. And we get our outermost shell. And we get, I'm going to make these electrons a different color just so that we can keep them straight. What do I think for a non-metal? How about red? So these are fluorine's electrons. 6 remain unshared, and then it shares its 7th. And what we can see is from the perspective of the fluorine atom, there are 8 total electrons or full valence shells, and so he has as much electron interaction as he can have. From the carbon's perspective, let's, well, carbon is black, we can keep them black. Now, it has more electron interaction than it did before, 5 instead of 4 electrons, but it still has empty space. So what that means is, as this is forming covalent bonds, it can form more covalent bonds. Let's look at that. I want to just change back to red here so that I can keep all my fluorines looking a little different. So here's a plus 7, and then that one would have its 7 electrons, sharing one of them in a covalent bond, a shared pair of electrons between 2 atoms. And there's room for another one up here. 2 electrons, 4, 6, and then there's your shared pair. And then finally, room for one more fluorine. So now if we consider this, we have 4 fluorines. That's why it's tetrafluoride. Tetra is the prefix that means 4. Sharing electrons in these covalent bonds with one central carbon atom. If we look at the fluorines, they all have their maximum amount of electron nucleus interaction, with 8 being attracted to the +7, and that goes up here too. And the carbon now has its maximum interaction. These are maximum interactions before a whole nother shell is formed, and as we know, as soon as we go to form a whole nother shell, we have shielding issues, and as a result, atoms don't want to do that. So this is the maximum interaction they can have, and so this is a fairly stable molecule set up like this. If we were to draw this as a Lewis structure, we would put the carbon in the middle. We would put one stick. Each stick represents a pair of shared electrons. So this stick right here represents these 2 electrons. And then we would put fluorine at the end of each stick. So each stick represents a shared pair, remember that means 2, of electrons or a covalent bond. And then each one of these fluorines still has their remaining unshared 6 electrons around them in the Lewis structure. The properties of these kinds of molecules are really complex. See, this molecule sticks together and flies through space like this. What it's going to do in terms of its melting point, its boiling point, its hardness, all those kinds of things really depends on a lot of factors, including the amount of the types of atoms involved in this bond, as well as its shape. So that's what we're going to talk about in the next upcoming videos. But for now, a covalent bond is when nobody will give up their electrons, so they have to fight over them or share them in between. And we can look at why using the Bohr-Rutherford diagrams, or we can come up with the more simple representation using the stick diagrams.